Well, let me tell you a little bit more about him. He's obviously a great engineer. He's a professor at Georgia Tech. He's a Vietnam veteran. He flew. He was an aviator, an Army aviator, a great civil service experience for the United States Army, basically supporting dynamics, engineering. He was involved in the Comanche helicopter. He was associate tech director for research and technology development for AVRACOM in the 1980s. And again, he's a professor at Georgia Tech today, a well-respected professor. He has come to our session many times in the past, and people flock to that presentation because we learned so much about lessons learned on the aircraft. But since he has so much to talk about, I think I'm going to let him take the floor, and he has a lot to show us on the future and what can we learn from the past aircraft. Without further ado, Dr. Schrage, you have the floor, sir.
Yeah, this is the quote from John in the previous one is really very applicable to what I'm talking about, where he says life is live forward, but understanding is backward. And that's really what I'm trying to do over the last couple of years, is to try to reflect back on a lot of lessons learned over the years. And I started this about a year or two ago, and actually I'm writing a chapter in the book that summarizes a lot of this. But I got a lot of material in here, so we need to go fast. And these are really addressing the AHIP OH-58D, LHX, and RAH-66 Comanche. And those were programs that I was heavily involved with. Obviously, I was involved back to the UTTAS and AAH and those programs, CH-47 as well. So I have the next chart, and I want to go through. Oh, by the way, Dr. Bill Lewis, who many of you know, who's really been responsible, I think, for the resurgence of advanced development in Army Aviation with something like the JMR and everything. And Bill and I go back a long time, and so he's contributed a lot. The paper itself got a lot of the details in it. There's a few things at the end I want to get to about the Comanche lessons learned, because these are things I think that are also very applicable for the future vertical lift. So next chart. So this is what I'm going to try to cover, a little bit about backgrounds, but I've got two charts I won't go through. I want to talk a little bit, I'm going to skim through the successful Army aviation development efforts, and then also some lessons learned from AHIP and that. The UTTAS and AH I kind of addressed last year. But I want to talk about this necessary synergy between the user, developer, and industry, which is very, very important, and something I think has been missing in Army aviation for a number of years, and hopefully it's getting out of that track. So I think that's important. Next chart. Like I said, I got involved in some of this air mobility operations and development of it back in the late '60s, and really the helicopter as you know, as its role, it really became the helicopter war, as you know. And basically, a lot of the stuff was learned in the country and how to use existing assets, but it also provided the information for developing the new aircraft. And at that time, in the early '70s, that was the UTTAS and AH, which eventually became the Black Hawk and the Apache. And so that was a very important part of it. The bottom one here is I'm trying to really get to the fact. I'm going to spend some time on the AHIP OH-58D, but Frank Harris, who's contributed to the paper and everything, has documented that very well, but there's some good lessons learned there. And then I want to end up with some of the Comanche development and how these things would fit FAR, because these are both scout attack type aircraft that's what FAR is about. Next chart. We're going to flip these fast. This is something I've used before. It's kind of cute because, you know, air mobility started with basically moving people. And pretty soon you needed to find out that the Huey provided that, but you needed to have gunships. And then pretty soon you needed to have scouts. And pretty soon you needed new attack helicopters. So this is something a friend of mine gave me one time, and I thought it was kind of good. Let's go to the next chart. This is just something I'm not going to go through because Rasmus's already covered it. Next chart, this is kind of my background experience. The next chart is Bill Lewis's. Go to the next chart. Okay, and Bill's, like I said, I think Bill was involved. We had an overlapping between Bill, myself, and Charlie Crawford as far as the development. I've got some charts out of here that Charlie presented at his Sikorsky lecture in '89, which are applicable to some of this as well. So next chart. So these are the programs that were successfully developed during the 1970s and early 80s. Unfortunately, there hasn't been an Army Aviation successfully developed since then. There's been modernization of some, but there's been a lot of false starts. And that's one of the objectives of this paper and lessons learned is to try to hopefully kind of do what John talked about, that, basically understanding is backwards. And so you need to look back at that. Next chart. We're going to keep flipping these, so be prepared. This is the UTTAS. Flip the next chart. This was in last year's, and it's in the paper. Anything that's in the paper. And I also understand that this presentation will be available for a year. So as I go through this, if anybody's got any questions about what's on any of these charts, feel free to send me an email, and I'll try to respond with more detail. Next chart. Next chart. This is just the development of the UTTAS. Next chart. And, there were 2 aircraft, 2 competitors. This is the schedule for that. Next chart. And then this is the AAH, which became, it talks about how it got started. Next chart. And, I show the 2 competitors in this because, the amount of changes that took place in the UTTAS in the development programs is amazing. If you look at those things and you would say, well, how did those programs ever get through that with all the problems, all the changes? And that's a big impact of what I'm trying to say here is that the helicopter still got a lot of things in development that have to be solved through flight testing and lessons learned. Next chart. Down selection, go ahead, next chart. I've shown you the schedules for these. If you can't find them, this is kind of shows the development. I was there. I arrived there in early '74, and was at AVSCOM, RADCOM 84. So that was kind of the heyday. It wasn't only AVSCOM. We had aviation research and development for a period from 1978 to 1984, which had a big impact. Next chart. Now, I did this last year, so I'm not going to go through these, but I tried to break the UTTAS and AAH programs into technical and management problems. Next chart. So that was covered last year. Next chart. A couple of them is this one chart, and this is a chart that Charlie Crawford had in his Sikorsky lecture. I helped prepare it along with Dr. Dave Peters, who many of you know as well. But to me, this is a problem, and it's feedback and feed forward loops. And the thing that for years, and this conference that, the Vertical Flight Society, people address pieces of these things, but they don't really address how do you integrate this stuff. And that's really the Achilles heel, is how do you do this very multidisciplinary, interdisciplinary integration? And that's still the Achilles heel, I think, of rotorcraft. We started programs. I was involved in one in the 70s called 2G Charlie, second generation comprehensive helicopter analysis system. Then we ended up, we have RCAS, but still we don't have really that good of a way of addressing these interfaces. Next chart. This is the 4 candidates there. There's a couple things. Next chart. They all had to raise their rotors, which is something you would think would be very similar. This one happens to show the vibrations on the UH-61. If you look at that upper left-hand one, you'll see that the vibration was quite high before the rotor was raised. Now, Boeing did raise the rotor for the Navy competition, but by that time, it was very hard for them to recover. If they would have raised it during the Army competition, I really think that it might be that Boeing has the bulk of the transport airplanes in the world. Next chart. One of the big things was that everybody learned is that, retreating blade stall has always been the Achilles heel of helicopters because that kept them from going too fast, as you know. But in reality, with cambered airfoils, it became more of a problem, not only with the retreating blade stall, which is still there, but really with this advancing blade. And every helicopter program I worked on, especially UTTAS and AAH, they all had a problem. Obviously Sikorsky went to the swept tip. Hughes ended up going to the swept tip. There's the team of government and industry that worked at UTTAS and AAH. There was a lot of collaboration, a lot of exchange of information. That's how a lot of the problems got solved. In many cases, Sikorsky was always the first to make the change, and then the rest of the companies kind of followed. Next chart. And this just kind of shows, the plotter on the left shows, kind of a stall flutter type thing. And stall flutter, as you can see, in 270 degrees to 360, that's where it occurs, but at least it gets out of that, And then the right one is the pitch length loads that you get with mock tuck. If you use cambered airfoils, Boeing has tried to use reflex over the years, and that's helped with the steady part of it. But really, the dynamic loads you get on an advancing blade, something sometimes called mock tuck, is a critical problem. Next chart. Let's keep going. This is the fact that the attitude change with a fixed stabilizer on the back of the aircraft affected just about all the four competitors. And as a result, they moved to a stabilizer. Once again, Sikorsky moved to a stabilizer. And then we ended up solving the problem with the Apache prototype by doing the same thing. Next chart. And that's what's shown on this chart. The phase one of the Apache, they had problems, so they decided to go to a T-tail. And that solved the transition problem with the attitude change. But once you got to high-speed flight, the tip vortices and foreperev from the main rotors excited the whole tail. And as a result, the loads were so high that even the tail rotor fatigue loads were affected by the bending of the vertical tail. Now, this was something that if you read some of the books by Hughes or somebody, it wasn't a big problem. I guarantee you this was a showstopper. And if, as you see in the last bullet down here, if it wouldn't have been for a joint team of Army, industry, this would never say, we would never have an Apache helicopter today. That's how serious it was. Next chart. I'm going to go through these. I'm not going to go through these charts, but these are from Charlie Crawford's Nikolsky lecture. And each one talks about each of these four prototypes and what were the flight test problems and what were the design changes. So just keep flipping through them. If anybody's got questions about those and want to get a hold of me, I can get you information. Next chart. And that's the YU-861. Next chart. That's the Y-863. That was the Bell prototype. Next chart. And that was a Comanche. Next chart. The Apache. Next chart. I'm not going to spend time on this, but the Chinook, I spent a lot of time. I was chief of structures and aeromechanics at the time when we were doing the modernization program, and it had a lot of vibration problems. It still got vibration problems today, but it's been a very capable aircraft. But these are just a list of some of the problems there. Next chart. A weight estimation is always the big problem. This is from Charlie's Nikolsky lecture. Next chart. And what it shows is that he shows that what the weight estimated was from the development spec, what it actually turned out during the government evaluation. Obviously, it's usually higher because the government is less optimistic. And then finally, what happens in first production. And you see most of them continue to go up somewhat. One thing about the Black Hawk was that Sikorsky aggressively went to a weight reduction going into transition towards production. And basically that had a big impact. Of course, the government gave them an incentive of so many dollars per pound they could save in weight. In fact, they took a lot of weight out and it worked out well, but I think some of it might have been put back in for fatigue lives. Next chart. Next chart, I'm going to go. You got to keep going on this. This is just showing that Black Hawk weight history, and you can see that it was pretty good. Obviously, if you have that weight empty low enough, that gives you the growth. Every helicopter is going to have growth if it's as versatile, if it's going to increase things, the external stores on this one, and you're going to need a bigger engine. So those are the history that has to be learned. Next chart. Now this is a good chart for this is the Kiowa and the Kiowa Warrior. And the thing was that Bell made a lot of these changes during the development program. Okay. I mean, they basically had a lot of things going on in commercial R&D and stuff, but they basically really put into the stuff. And that's why you see it really flattens out and how things growth in weight went up empty. But the big decision was when they went to the C-30 engine and 4 blades, which I'll say something about later. It's not the 4 blades, though. It's the hingeless rotor that really was the cure. Next chart. And then this just shows some other missions. So it kind of shows where the mission gross weight comes in. Next chart. Okay, then we go to the AHIP. Okay, and like I said, I flew both of these in Vietnam. I flew mostly the OH-58, but I was asked to do a comparison with the OH-6, and we had an air cav troop. I was the S3 for the 13th Combat Aviation Battalion, and I did in-flight evaluations with the air cav troop, flying both the OH-58 and the OH-6. This was in like 1970, and we flew down into Human Forest, which is part of the Delta where you definitely flew a lot of nap of the earth. Next chart. And then, when it was decided for the AHIP, the mission was different. This was the whole idea of using it as with an attack helicopter. And I also got the A-10 on here, laser designation, and the use of a mass-mounted sight. Next chart. So this CONOPS was different than what it had been for just the Scout. Some of the background on the AHIP solicitation, you can read this. Like I said, Frank has done a great job of documenting this in several papers, as well as Mike Kawa. Next chart. So these are the candidates, and you see the mass-mounted sight in the lower right-hand corner. And you got to realize that what was done in that AHIP program in just a few years was amazing when you consider that it was a complete remake of the aircraft. In fact, Bell told me it's been a lot cheaper just to build brand new instead of trying to take an OH-58A airframe and convert it. Next chart. Bud Forrester, who many of you know, he was the colonel at the time. He became a lieutenant general, and part of it's because of the success of the AHIP. But basically, it was the first of first digital cockpit, first digital fuel control, first complexity composite rotor blades, composite rotor head, all these different things. So to think it was, and it was a fixed price contract, okay? To think that all of these things came in very easily it's a tough story. Next chart. And so, because it had that growth, because the OH-58D was designed with enough weight margin and power margin, it could do a lot of other roles. And that's how it became the Kiowa Warrior. And that had a big impact on it. Next chart. This is a chart that Frank shows how scouting went from balloons in Civil War, I guess, all the way up to mass-mounted sights. Next chart. That's in his paper, by the way, which is a great paper. If you haven't got it, you can get it off of the Vertical Flight Society. This is kind of the development schedule. Next chart. This is kind of interesting because, there was a lot of desired requirements that were in that AHIP solicitation because we knew that we wanted something, they'd gone through so many iterations of trying to get a new Scout. We went through that so many times that we really had things that we knew coming out of Vietnam, what we really needed. And so basically there's the air vehicle and the mission equipment. And today, this was very important for AHIP. That's one reason I always think that AHIP is a good example in the OH-58D because it was really driven more by mission equipment than it was by aircraft. But if you wouldn't have had the growth in the aircraft capabilities, you could have never made it into what it was. So that was very important. And so basically, as you look at the right chart here, the near-term scout helicopter, that's the name of it, the AHIP was the program. You can see that Sikorsky had, not Sikorsky, but Bell had a lot of options here, a lot of it trying to decide which way to go. Next chart. I'm going to go through these quick because understanding the requirements is such an important part. And for FARA and for all the FVL, the iteration on requirements and the understanding between industry and government, but not just government contracting. It's got to be the technical expertise. That's the key thing, and that's a very, very important thing. But this started off being the requirements, but you can see at the top, the target acquisition and everything was at the higher part of it. Next chart. And this is interesting because this kind of evolved, and the only thing that changed a little bit was the precedence of the desired requirements. And if you look on the left one, that was a period of 1980, and then the final one in 1981. And you can see that this was a tough choice for industry, a fixed price contract. People like Frank Harris and the people at Bell, they had to convince management and Textron that we need to go after the desired requirements. And so they basically went through there. Here's Frank Harris's quotes on that from his paper. You can read them. Next chart. So they had a choice that they were trying to decide. And there was, the Mini, which was taking just a bare bones modification of the OH-58A to the C. And then there's the MIDI, where they bring in a new four-bladed hingeless rotor. And then finally, the Maxi, which you had to have the moment and the power, the hub moment and the power, to really make it an agile mobile helicopter. Next chart. And so this is kind of sort of the system spec. We put in the system spec. I purposely put this in there based on my experiences in Vietnam. We wanted an agile, maneuverable helicopter because my experiences in Vietnam, the OH-58 two-bladed rotor would not cut it for what we were looking for. Next chart. And, Nap of the Earth is something that now we can call urban operations is going to be a very tough environment. And, every helicopter program I worked on, there's some maneuver requirement. We give them kind of steady state performance requirements and everything. But the maneuver requirement on the UTTAS and AAH, it was called the UTTAS maneuver, a pull up and push over. In the case of the AHIP, we couldn't really specify too stringent requirement. And it's going to be very important to have this on the FARA and these aircraft as well. Next chart. So we did put this in here and we shaded the desired area. This was to get the pitch, roll, and yaw, control power versus damping. That gives you one element of the agility problem that you need, okay? And we made it desired because it was a fixed price contract. We couldn't force the industry to do this. Next chart. And this all has to do with the fact of what kind of head moment, what moment you have. And, basically the teetering's a great helicopter. I flew the Hughes, I flew the Charlie model gunship, I flew the OH-58s. However, it's not a good low-speed agility maneuverability helicopter. And this is kind of explained here. And the plot on the right, it kind of shows you where the OH-6 was, say, compared to the OH-58, which would be down near the Cobra. Next chart. The thing was, there was a lack of understanding of what really the scout pilot needed. And so basically Frank Harris and Ted Hoffman, who was a program manager, I suggested they go down and talk to the scout helicopter pilots down at Fort Rucker. They went down there, and it so happened that they were coming back through Dothan, and I was going through Dothan to go down to Fort Rucker. And they said, we really learned a lot. And that thing that's underlined here is virtually to every person they talked to down there, they described a duck and run situation that from start to finish took something less than 15 seconds. However, they went back and they said, well, we haven't designed for that. They went back and took their 206 LM, which was their hingeless four-bladed model. And they found out that the C-20 engine just was not big enough. as you can read here. The maneuver required what was their maxi solution. Next chart. So basically, this is a good chart that summarizes from Frank's viewpoint, and I think I agree 100% with it, is that agility is not number of blades. It's having excess power. Hub moment capability that I showed is important, as well as blade loading coefficient. The duck and run was the name of that maneuver. That's in the third bullet on the bottom here. Next chart. Okay, so this is the stuff that went into the AHIP, and you can see these are the that made it, and they really satisfied the desired requirements that the Army was looking for. Next chart. Keep going. We're going to go fast here. Okay, the mass-mounted sight. There's a lot of stuff in the paper. We spent a lot of time working this. I wrote some papers on mass-mounted sight stability a long time ago, and I think they're referenced in here as well. Next chart. They're in the paper. Next chart. And so this is what man-machine. This is the weight breakdown in 1981. Next chart. Let's keep going, because I think I'm going to run out of time, and I really want to get to the Comanche. Next chart. Okay, these are the other ones. These are all in the paper. There's the cockpit integration. Very, very tough. Next chart. And next chart. This is going to go some more with designing that mass-mounted sight. One of the big problems there, you know, this was before we had complete open system architectures and things. We had the 1553 data bus. But when you look at all the boxes that were put into the OH-58D, and then when they went to the Kiowa Warrior, it went from 90 up to 137. You can see what a nightmare it was for the mission equipment to try to integrate all that. Next chart. This is mass mount sight. Next chart. Let's just keep going flipping, because I think I'm going to be over time. A lot of stuff about the mass mount sight. I wrote a paper that describes a lot of this. It's a reference in my paper. Next chart. And this had to do with what ranges you could get. The vibration is very important. Can you imagine putting something above a rotor system? And one thing that McDonnell Douglas had, which they developed with the Army, was called the IPSU as a good vibration system. Next chart. Next chart. That's just a modeling and simulation we used on the source selection board. Okay. And let's go ahead to the next. Oh, let's keep on this chart for just a minute. These are the references on the bottom. I strongly recommend you read if you haven't seen them. One by Frank Harris, one by Mike Kawa. And then there's a book that PEO Aviation put out that's really good. If you haven't seen it, most people haven't heard of it, but ask for it. It's a good book. Next chart. Okay, development of the AHIP. This is an important chart because what Frank said, and I agree 100%, is the right people were in the right place at the right time. And the thing is that technical experts from the government have to be very credible with industry and working together. Once you turn it over to program management, innovation and creativity goes out the window. So it's very important on this chart to do that. Next chart. We got to keep going here. That's just going to the Warrior. Next chart. Bill Lewis had a big role in that. Next chart. This is a chart I did for NATO requirements, and it goes into the LHX. Next chart. Just keep flipping charts here, and I'll hit a few points. We did use on the LHX at the beginning of the Comanche program a tried and true approach, for formulation, the trade-off determination, trade-off analysis. Now that they have the JSIDs, I think this is less effective and more shallow. Next chart. Next chart. This is the concept formulation program. It's kind of interesting because let me just say a word about this chart, because when I was head of director for advanced systems in science and technology, we started the concept formulation about 82, 83. And basically we gave contracts to the industry, what was needed for LHX. And if you see on the right, it's kind of interesting because the coaxial that Sikorsky proposed, you can see the tilt rotor, obviously Bell proposed, and then Boeing and Hughes proposed something. We could have had the coaxial compound in the LHX program, but we didn't for a couple of political reasons. And go to the next chart, and I might hit on something on that. Next chart. This is just, we had a good science and technology program. We could justify it. The LHX was soundly, the user was soundly behind the LHX. They'd done a mission aviation analysis. They knew they had to replace the helicopters in Vietnam. So we had a really a good support between the user and the developer on the LHX and into the Comanche. Next chart. Next chart. These are just some of the tools we use. Next chart. Competition. Yeah, this is a key chart because what happened, I left St. Louis in 1984 at the beginning. And basically at that time, it was still open to advanced rotorcraft configurations. But as you know, there was a JVX, which became basically the B-22, which was good. But it was not the answer for the LHX, not for the light helicopters and things that they were going to do. Just like the tilt rotor is not really a viable candidate for FARA. The tilt rotor is a great aircraft. In fact, I even went to Congress and briefed them that the B-22 was a good solution. But basically, the Army didn't want to spend $5 billion because their aircraft in the JVX was special electronics mission aircraft. And, you know, the Army's built around killing people, right? And doing things like that. So next chart. Concept formulation, next chart. Just keep going through these. I think we're going to be out of time. I want to get to the last two charts. This goes through the Comanche program. Now, one thing about the Comanche program, the government, which I've been over to review over the last year, they had documented a lot of lessons learned. I really wish that Sikorsky would have documented more lessons learned. They did on some things like the air resonance problem. They solved it with active control. But if you go through, and I'm going to have to just flip through all of these to the end because we're going to run out of time here. Next chart. This just shows you prototype testing. Next chart. A little bit of history here. Next chart. Comanche was a complicated system, you know, probably the most complicated. In fact, when I left, we put the LHX people, the OH-58D Kiowa Warrior people, we put the best mission and equipment people we had into the LHX program office to start with. And that was probably good because I think that worked out. But you can see how complicated the system was. Next chart. And that's just some more integration of these. Next chart. Next chart. This is the cancellation of it. Next chart. Go ahead to lessons learned. As I said here, that previous chart, lessons learned, there's a lot of lessons learned, and I'm hoping that sometime following the first of the year that we as a team, industry and government, can spend some time with the people that are developing the FARA and to some extent the FLAR, but really help with some of these lessons learned, because just as it was talked in the previous, life is lived forward, but understood backwards. These are a whole list of things that public domain, they were presented at the University of Alabama, Huntsville Professional Development, and it's the government's view of lessons learned from the Comanche that I think everybody should have a chance to review. But at the same time, as I say in the bottom here, it's recommended that the FARA PMO sponsor a technical workshop in spring 2021 on applicable lessons learned from the Kiowa Warrior and the Comanche. And I hope something like that can happen. Next chart. Just keep going. We're running out of time. There's a whole bunch of things. The main rotor system, which is still at the most critical thing on a helicopter, and it's still the one. Back in the 1980s, Bob Armiston and the guys started a program called Integrated Technology Rotor. It was supposed to lead to flight testing, and it never did, which was probably the biggest mistake I think the Army ever made, because industries today, designing a bearingless rotor is still a challenge. Next chart. This weight chart's very important right here, because what this shows is that because of the design not being completely solved technically, not just the mission equipment had some hiccups, but the mission equipment was in a lot better shape than the vehicle was. If you look at that last thing there, that big jump in gross weight was due to main rotor system having to be redesigned. Next chart.
Dr. Schrage,
And
we are about 6 minutes or 7 minutes over time. If there's any way we can get some final comments from you, I do apologize to cut you off, but we have another presenter waiting.
Okay.
I hate to do this to you, sir. There's so much good information here. You'll need probably 3 hours, really. Can you comment on some final comments, sir?
Yeah, if you can go to the last chart, the summary, just go to the last chart. Can you do that? All right, summary and conclusions. You know, I tried to trace the history of Army aviation development from the 70s, where appropriate, identify lessons learned for both successful and unsuccessful development. The conclusion of this was that, you know, Army aviation has positioned itself largely through the successful FVL JMR program to look at new concepts and to solve the tension between designer and developers and iterate. It's very important to have that type of collaboration, which is talked about. Sorry, I took more time. It's hard. I had a lot more charts, and sorry about that, but I'll be glad. Anybody that wants to ask a question, or if they want to send me an email, I'll be glad to highlight anything that's in this presentation or in the paper. Thank you.